Hello. After the last video, we now have the basic functionality of how our species object is specified. In this video, we will describe how you can input the parameters that govern your simulation. Once you've decided that your code has all the model behavior you want to study, you generally want to change the C++ and CUDA code as little as possible. This is to make implementing the analysis of the model easier. An important part of model analysis involves trying to understand how inputs to the model affect its outputs. Parameter sweeps, in which the input parameters are changed one at a time in different simulations, provide a common example of such analyses. When the model inputs are numerical parameter values, ideally you want to minimize the effort it takes to change the model inputs. SPEGG simulations use two core sets of inputs. First, you have input that describes the overall simulation's configuration, such as how many patches you are simulating, how many iterations you run the simulation for, and your random number seed. We are going to put these inputs into a simulation.conf file. The first setting is the number of steps over which you are going to run your simulation. We saw this variable earlier in our simulator source file. The second setting, ndems, is the number of dems or patches over which you will be simulating. For a more detailed overview of this, please refer to our manuscript. The next set of variables, num-biotic variables and num-abiotic variables, describe the number of dynamic environmental variables of each type in your model. Loosely, environmental variables are those variables whose genetic evolution is not modeled. Thus, they can be everything from abiotic variables, such as the temperature or water level on a given day, to biotic variables, such as the density of a resource or predator species whose evolution we are not tracking explicitly. Since the simple single-species simulation we are using here does not track environmental variables, both of these will be set to 0. Finally, you will have to manually set the value of the random number seed for your simulation. The parameters and their values are stored in the text file called demconfig.txt. This input file facilitates surveying different regions of parameter space. This text file uses what is called a structured configuration file, which allows you to group key model parameters together. For example, our simulation includes model parameters that pertain to the genotype-phenotype map. Often, we will want to organize our input file so that the parameters that specify a given genotype-phenotype map, such as the allelic weights associated with the various loci that contribute to the phenotype, are grouped together. The input file demconfig.txt uses the third-party libconfig library to accomplish this task. In the following few minutes, we'll try to gain a conceptual overview of each section of our structured configuration file by looking at a pre-made template. At the most coarse level, the structure of demconfig consists of two groups of input data: variables and parameters related to the genetic architectures of the traits we are modeling, and variables and parameters dealing with everything else. Let's start with the segment of the configuration file dealing with the genetic architecture. In the third-party libconfig library, data are grouped inside brackets. Data inside curly brackets form a further self-containing group. Thus, each species' genetic architecture is modeled as a group. The species genetics setting therefore consists of a list of such groups, representing the genetic architecture of separate species. Because we are only modeling one species, we only need to have one group of input data, namely that for species 0. For each species genetic input group, we will specify several properties. Let's start with specifying the number of loci we are modeling, which we do by typing our number of loci equals some number. Each locus we model will have further input parameters associated with it, including its mutation rates and the magnitude of the mutation. We will also need to specify the recombination rates among loci, the number of phenotypes or traits we are modeling, and the names of those phenotypes. Each phenotype will have associated with it a genotype-phenotype map. Here is an outline of the species genetics sections of our input file. We can think of these as coefficients of an equation that specify what phenotypes result from what genotypes. An important consequence of setting things up this way is that we can now have different input parameters for different demes. This allows us to conduct, for example, sensitivity analyses that look at the consequences of alternative genetic architectures in parallel. A detailed example of this for our genetic drift example is provided in the online tutorial. As you will see, this specifies that we are modeling 3 loci and 3 phenotypes. There is free recombination among loci, and each locus has a mutation rate of 10 to the minus 4. The loci vary in the effect of the mutation on the allelic value, which we assume is a continuous number. The next section specifies the genotype-phenotype maps. As you can see, for every phenotype, we specify how many parameters are associated with each map, which parameters are part of this association, and the numerical values of these parameters for each deme. Notice that we can specify that a phenotype is not genetically determined by setting the coefficient of allelic effects, for example, to 0. The next part of the deme config input text file consists of parameters that are used for the non-genetic component of our model. These can be parameters like the strength of selection or the rate at which physiological processes modify an organism's vital rates. Again, we group the input parameters separately for each species and create a list, which we will call species data, that put together the group parameters of each species. For our example species, we will often want to specify some variables that are not subject to our surveys of parameter space. By convention, these are called species-specific values in the model. They mostly aim to help manage the code rather than modify the predicted trajectory of the simulation. For example, this could be the index in our array of phenotypes that belongs to a given phenotype, such as the fecundity rate. We will want to specify the number of such values and their names. Next, for each species that we model, we want to specify the number of parameters and the names of those parameters. The final segment of this section of the deme config input file consists of specifying, for each deme we simulate, what these parameter values are. We will group the parameter values into different demes and then create a list of those groups, which we call deme specifications. More elaborate versions of these configuration files can be found in each of the examples we present. But let's briefly do a high-level review of what makes up the deme config input file. We have the section Species Genetics, which groups the genetic inputs for each species. These genetic inputs consist of specifications of the loci we are modeling and their genotype-phenotype maps for the species. We then have a section for all the other species-specific inputs that are not related to the genetic modeling. These include variables whose values are shared across demes, such as those used for bookkeeping, and parameter values that we vary across demes to survey parameter space. We create a list of these groups for different species called species data. In addition to these 2 core input files, depending on your SPEGG model, you might want to configure 2 other input files. The first is an environment config.txt file that specifies the numerical parameter inputs for the environmental variables. That is, those state variables whose genetic evolution we don't model explicitly. This input file largely resembles deme config.txt. Here is a sample environment config file based on one of the case studies in our manuscript. However, because the simulation model in this tutorial doesn't involve environmental variables, we won't go into this further, and it won't be included in the demo video codebase. Finally, an optional input file specifies any non-zero migration rate between demes in your SPEGG simulation. You can find an example of this in the repository's co-evolving species entry. This input file is not needed for our present simulation, but I mention it in case you want to model migration in your future simulations. In the next and final video, we will discuss how we can bring everything we have discussed together. Thank you for watching, and if you have any questions, please shoot us an email via our mailing list, speg-users@googlegroups.com.